Before we start, today Krishna will give us presentation about LMFP battery and battery material synthesis. And before before you present, I would like to briefly mention our goal, and our goal is learn, to ask questions, explore, and grow our community. Okay, uh, Krishna, if you want, we can start. You can start.
All right. I'll be talking about a cathode material which has come up recently. Not recently, it's been in trend since like 10 years. People have been researching about this since some time, but it's been a recent approach into the material. I'll be talking about why this is of interest and how can we achieve this interest of ours going forward. So before I jump into LMFP, this is a quick glance about like the history of batteries. We would all know it all started with like voltaic cell where zinc and copper were piled up together with like wet clothes, and we were able to derive some current, not much, and then it was improvised by Daniel with the Daniel cell, and then we have Leckland cell, and then somewhere in between uh, lead battery was discovered, which is still being used in like cars and stuff. Then we had nickel and then so on. And the first and foremost lithium battery was introduced by Sony from Japan in 1991. And it was a very big change because lithium rechargeable batteries were not trending at that time. And it was mostly like we were just using batteries and then they were just waste or byproducts. And recharge and recyclability became a very big trend towards the late 90s and the early 2000s. And that's when like Sony dropped lithium ion batteries from Japan. And since then, we have been focusing on the ability of lithium to go back and forth in electrochemistry. And because of its stability, we are trying to dope it with further material and mineral and get even more better performance out of it. I'll go more into that later on, but this is just a quick overview of batteries so far. So now we come to LMFP specifically. So as I said, 1997. The first reported LMFP was founded, and then since the arrival of LFP, it's been used extensively in the market. Most of the EVs right now also use LFP as its primary batteries. So LFP is known for its stable capacity, stable life cycle, and just dependability overall. Um, since then, the research, 2006 is where um, the uh, life cycle, I would say, of LFP was being researched upon and tried to make it more efficient and increase. So they tried adding amine, manganese. 2006 is the first time they did it, and since then they have been researching extensively upon the reactivity of manganese and iron together in the structure itself. So, okay, now what is LMFP? So, LFP, as we would know, is lithium iron phosphate, and LMFP is just manganese doped into the very structure. So, LMFP belongs to the olivine phosphate family. Olivine phosphate family is derived from the word olivine, which is a mineral, and it has a structure similar to this. And because of this structure, it is very stable. And this structure is actually useful in all electrochemistry as well. I'll go more into that when we reach upon this slide. But yeah, olivine is just because of its structure. And then why do we have to include manganese? Why can't we include any other element per se? Because there are a lot of like elements that we could include. Um, in in this case. So we pick manganese because its redox reaction is higher than iron itself, which is able to generate more energy density. So for the same stability and the same structure, we can get a higher density, which can also improve like our life cycle and the energy output per hour. So generally speaking, the LFP batteries would have around 130 watt hour per kg, and LMFP, according to lab results, would be able to generate like around 160, 165 watt hour per kg in terms of theoretical capacity. So, and why manganese? Manganese redox reaction is slightly higher, not that high, not there's not much difference with between iron and manganese. So that's the first reason why we pick manganese. If we pick any other element which has a very very different redox reaction as compared to iron. Maybe the difference of between the redox reaction, if higher, could lead into complications and could lead to a wider Fermi band, which makes it hard for electrons to travel into the conduction band. So this reaction, even though has higher energy on paper, it is quite achievable. So that's why we pick manganese of all elements because it's convenient. And again, just adding manganese to the structure itself does not solve all the problems. Iron is stable itself. Manganese has energy density, but it does not have stability. So we have LMP cells, which are lithium manganese phosphate cells, but they are not used extensively, even though they have high energy capability as compared to LFP, because they're not stable. They give into thermal, they have thermal runaways, SCI growth, and stuff like that, because it's not stable. And I'll go into why they're not stable. So that's just a uh, overview of LMFP. You see here, I have the comparison between um, in lab conventional LFP cells on the left hand side, and on the right hand side, we have in lab like conventional. These are not conventional, these are made by ourselves, but I've not been able to achieve the theoretical capacity so far. But these are this is how a general cycle of LMFP cell would look. And if you can compare on the left hand side, you can see a very distinct and a very sharp drop of voltage. But when you see the right hand side, you can see a slope when the charging and discharging happens. And this plays an important role um, in electrochemistry as well, because if we have a sharp drop in a cycle, it is considered as most stable. Because there is a slope here, it determines like there is a difference between the iron and the manganese redox reaction. So this, if it was a straight line as LFP, it would have helped the cycling stability. But as it is not, we have to play around with the ratio of manganese and iron incorporated, which plays a very huge factor again. So, what are the challenges in LMFP? It has poor electronic conductivity, because again, this can be of can be due to several reasons. And the first and foremost reason would be the structure itself, because it's an olivine structure. It is in crystalline lattice, and the structure itself is um, like this uh, crystalline type. And if you see the end nodes in the first figure A, if you see the end nodes with like small dots, you could determine them as phosphate ions, because phosphate ions generally surround the metal ions, and that's how the crystalline structure is formed itself. So the phosphate ions itself are insulating, and they do not allow conductivity. So that's the first reason why we have poor electronic conductivity in LMFP. And there could be many other reasons as well, due to the particle size itself, could be the structure degrading because of Yarn-Teller distortion. There could be several factors which affect LMFP's electronic conductivity. But again, this is the foremost reason why we do not see LMFP being used extensively in the industry right now. This is a very big concern. Second being, there are not enough pathways for lithium-ion diffusion because of the crystal structure itself. Um, the pathways are so limited; they do not have free space to move about in the structure. And then we have Yarn-Teller distortion. So what is Yarn-Teller distortion? So when manganese are in the stable state, which is manganese 2 plus, um, they are more structured, and they have um their valence, their conduction band is filled with electrons, and there is no lone electron in the valence band. But when it is oxidized to manganese 3 plus, there is a lone electron in its valence band, and because it has to survive with by itself, the structure gets elongated, if that makes sense. So what happens in quantum physics is like, when reaction happen and ions move from the lower state to a higher state, electrons can't just move up in their from the conduction band to the transition band um, with free will. They have to pair up with an existing electron, or they have to survive independently. And in this case, when it is excited to its transition band, because there is no electron available in its transition band, this ion has to survive freely. And because of that, stress is generated within the ion, which makes it elongate in a certain axis. So we could discuss about this further. Uh, Maybe I'm not giving the most clear example of Yarn-Teller distortion, but because of this elongation of the ion itself, a structural strain or stress is generated, which degrades the lattice structure and does not allow ions to move freely. Again, Yarn-Teller distortion could be advantageous for the structural uh, for ion transportation, because again the stress and strain creates new pathways for lithium ion diffusion as well. But after a certain point, this cracks or these new pathways can also hinder electrochemistry, electrochemistry happening in our batteries. So this is not quite straightforward. Um, there is a lot of tweaks we have to make with our ratio itself. This can be detrimental for our battery or advantages for the battery itself. That's why it makes this research so much more interesting. Something which can be harmful can also be advantageous for the battery structure itself. So again, as interesting as it is, not that simple. And um, the last thing I would say, which is a challenge in LMFP, is mixing of iron and manganese itself. So when we have a ratio of two different materials being mixed in a solution, you want to have the right chemistry and right distribution of each and every ions within the lattice structure itself. Something as complicated as electrochemistry needs to have even distribution throughout the solution, or the electrode itself. Because even though we measure out the right amount of material or the precursor, it would not relate to the end product itself, or end product could have um, polarity or could face polarization because of different concentration gradient throughout the structure of the battery. So again, so these are the challenges in LMFP currently. And to be very honest, throughout my time in research for LMFP, all of these challenges can be resolved by the synthesis method itself. So the only way to get rid of all of these challenges is how we make the product itself, how we synthesize the product. So in LMFP, if any progress is to be made, is by synthesis method. There is no other way to make progress for LMFP so far. So to understand how we can make LMFP, we can have two approaches per se. So we can have non-aqueous phase methods where we do not use a solvent or a solution. We just take all of the precursors, grind it together, and get LMFP, which is the most straightforward method. And it is used, it is widely used in the industry to make battery materials because solid state method is the most straightforward, can be repeated again and again, and can have stable results. So industry would prefer solid state method because it's cost efficient, repeatable, and can be generated in like huge bulk. Um, for lab-based synthesis, we have aqueous phase methods where we use solvents, and we try to make it more homogeneous, and we try to uh, play around with the morphology and particle size and stuff like that, which could actually help our battery material. So this is a quick overview. I'll dive into the synthesis method. So I use a co-precipitation method for my research, which is okay. I'll describe what is co-precipitation going forward. First is solid state method. As I said, we mix precursors, we ball mill, and the most important aspect of making or synthesizing LMFP is the temperature. So the calcination temperature is a very crucial factor for making LMFP. If it does not reach the right temperature, it does not get calcined, or the particle um, stays dispersed, do not agglomerate, and do not reach their potential and do not carbonize. So anything below 650 to 750 would not be apt, would not make it crystalline, and would not help it attain the olivine structure. Anything above 650 or 750 may damage the structure itself, may dissolve the carbon source inside the material. So 650 to 750 degrees Celsius is the temperature that most of the methods try to reach with the material itself. There has been several papers which have focused on the importance of temperature in LMFP, and all the papers state that 650 to 750 is the right temperature for synthesis. Again, it is scalable, low cost, and simple. Cons being we cannot we cannot determine the particle size because we are just grinding it. At the end of the day, there is no filtration or no homogeneity in particle size, so there is poor uniform particles. And because particles size are larger, lithium pathways will be longer because they do not have anything to penetrate through. Second method will be sol gel methods, where two metal salts are dissolved in a solution in an acid and they form a gel, and then they're dried, and then they're calcined at the same temperature around 650 to 750 degrees Celsius. The advantage for this, we get a more homogeneous distribution within the solution itself because the metal salts are being dissolved in a solution, and because of that we can understand like uh, the chemistry is happening with the solution, and because it's dissolving and dissipating, we'll get a more even distribution. Again, because of this, the particles can be nano-sized because it's a solution itself, and it depends on how you dry your solution, the particle size are going to come about. We can get good carbon coating with this method. Can be complex because we're getting a cell gel or a slurry. We are not getting a direct solution, and it can cost high because of the materials itself and the process cost. Okay, this is quite interesting. I like this method because this is the only method in LMFP synthesis which does not require high temperature, does not require high energy, so it's much more cost effective. We do not need a furnace for this. Um, so our material preparation is quite standard, where we mix stuff and uh, again, metal salts are dissolved in a solution and then sealed in an autoclave. And the autoclave is put inside an oven. And because of the pressure inside the autoclave, it does not have to go to a high temperature. Anywhere around 180 to 220 does the trick. And after we retrieve the autoclave, we get a general solution or a slurry. And because it's being synthesized in an autoclave, the advantage of using autoclave is it gives us a definite particle size. It can morph the molecules of the solution in different shapes. So papers have claimed nanoplates, nanorods, and mesocrystals perform much better than simple chemistry. As you can see here, this would be a general particle from a powder, LFP powder or LMFP powder, whereas C, D, and E are different shapes that you can morph your particle into. And because of this morphology, it also helps lithium ion diffusion. And lithium has much more area uh, to be stored in as compared to normal particles. So quite interesting. Can morph shapes of particles. Spray pyrolysis. So this again determines particle size. The method is quite standard. You mix solutions, make it a slurry, and then you have to pass it through a spray dryer, basically to break down the particles into nanoparticles again. Um, and then we have co-precipitation method where you have metal salts and then you have to reduce them or oxidize them to get them into the standard ionized form. And because you're playing around with acids to oxidize and reduce, it is quite sensitive to the pH scale, temperature, and again, if you over oxidize and over reduce, you have a chance of getting an unstable product. But again, uh, the key factor, the, the key takeaway from all of this is each and every synthesis method has its own advantage. Uh, None of this synthesis method can achieve everything that each synthesis method claim, and that creates a gap. If there was one synthesis method which could get nanosizing, scalability, reusability, or any standard that battery the powder could be made upon, we could have a simple synthesis method that each and everyone follows. But because there is no standard and each synthesis method has its own advantage, there is no go to paper or there is no synthesis method that we can just pull out and achieve the desired powder. So the electrochemical ability for each and every cell for each synthesis method also varies. Each claim by each synthesis method also varies. Some claim that it's the diffusion that's being limited, some claim that it's kinetics that's being limited. But again, each way we synthesize the product, it shows different electrochemical ability, which makes this research so much more exciting. Um, so these are the modifications which can be made to LMFP. Carbon coating. So nowadays we have carbon coated LMFP where the carbon is being coated during the synthesis itself. So the carbon source is added into the material as a precursor, and because of that, we have an amorphous carbon coating for each and every LMFP particle, which again improves conductivity because carbon is not in olivine form; it does not have a structure. So electrons use this carbon as why, as you could say, to conduct themselves through the structure itself. So carbon helps conductivity by providing this path, and it's also buffers stress because the structure does not have to do much load in storing and transferring lithium because carbon does it for the structure itself. And then again, after you have LMFP, because you understood adding manganese improves LFP structure, how about we add more ions into LMFP itself to make it better? So by adding ions like magnesium, titanium, and nickel, and so, people have observed they were able to reduce the yarn teller effect, which again reduces capacity and energy fade. It also improves kinetics. So further research are being done by uh, incorporating more foreign elements and stuff like that. Again, composites. NiCad batteries and LMFP batteries are being used together in sync, so both can match each other and could make up uh, each and for each other's disability and stuff like that. So there are also a lot of other modifications which are being made, namely gradient doping, where to reduce magnesium dissolution within the solution, um, people are trying to make the particle much more iron rich, sorry, much more magnesium rich in the center and much more iron rich in the outer core so that magnesium does not react with the electrolyte itself and dissolve within the solution. So this is just a summary. Uh, LMFP gains advantage by iron stability and manganese higher energy density, but it's not that straightforward. Along with this comes disadvantages as well, which we try to uh, address with our synthesis methods. So the key issues we try to address is low conductivity, lithium-ion path, and magnesium distortion. Because when manganese is in its higher energy form, which is Mn3 plus ion, it is quite okay and stable. But when it drops back to Mn2 plus, it is very likely to dissolve in the electrolyte itself, which then affects the SEI in the cell and also leads to electrolyte contamination, further leading to capacity degradation and stuff like that. Synthesis methods strongly affect performance. Carbon coating and iron doping improve conductivity and stability. As we read through different papers, papers have claimed 25% iron balance gives the best cycle life and voltage, but because this is very recent research, claims have been all over the place. People claim 80% of manganese is better. People claim 50% of manganese is better. So it just comes down to the synthesis method itself and the right chemistry. For me, I believe 8 is to 2 is the perfect LMFP ratio, where 8 part of manganese and 2 parts of iron gives us the best theoretical output. But again, the future depends on scalable synthesis. If we could find a synthesis method which can be replicated, cost effective, and can be used in industry, LMFP is the next battery to take over LFPs. And there could be research into recycling, hybrid, and solid state use of LMFP as well. So that's all from my side. I'm sorry if
Okay.
that was so
Does
much.
anyone have any question? Thank you so much, Krishna. Your
Yeah.
present.
I'm sorry if I didn't address anything or could not address anything or was not clear about any part. If you guys want to go through any of it, I'll be very happy because this is something
Thank you
I'm very
so much.
interested in.
Thank you
Thank
so
you.
much, Krishna. It was really amazing presentation. I was really amazed. I was not involved in any project related to LMFP synthesis, and that was really informative for me. I took some notes. I will look them after. But so far, you explain everything. Uh, I actually I don't have any question, but I just want to say thank you so much.
Thank you so much, Amit. Thank you so much.
Krishna, thank you for your great presentation. Thank you for your time. Uh, I have a question for you. First of all, the presentation was really good. Emre abi,
Okay.
Emre abi mikrofonunu kapatması lazım var mı abi? Çok ses geliyor. Teşekkür ederim. Ee, Thank you for your presentation, Krishna. It was really good, and you have given a lot of information about the production processes in laboratory production processes of LMFP. I just
Uh,
want your comment because you have all the time dealt with production methods in lab scale. What if
mhm.
what if we want to increase this into a plant? Which methodology you would increase? Which methodology you would scale it up? You will scale your method to a plant. I'm really curious about it because lots of methods, co-precipitation, sol-gel. Which
Mhm.
one would we choose if we have a mixing tank or a manufacturing one unit? Thanks a lot for your time.
That's a very good question, Mustafa. So that is one of another important reason why LMFP is not widely known because the synthesis method itself is so complicated. We do not know which synthesis route to opt for. Again, there have been many papers which claim the best synthesis method out of everything, but so far in the battery industry, most of the battery manufacturers use solid state sintering method to make battery material because first of all it's very straightforward, not complicated at all. You just mix things together, grind it, and it's about scalability. It's not about fine tuning your powder material itself because so far the powder materials are standardized and it does not need great electrochemistry per se. Because LFP has just one voltage peak that is at 3.2, whereas LMFP has two voltages peak. One is at 3.2, other is at 4.1, which makes it much more complicated electrochemistry. So it's harder to generate out of something as simple as solid state method. But I have read papers which are from 2024 and 2025 which have claimed that they have used LFP cells to make LMFP by solid state sintering method, which is very cool. If we can reuse and recycle spent batteries to make something much even better, which is LMFP, I think that's the way to go forward with. So, for your answer, I think solid state method would be better for industry as compared to lab scale processes. But again, we cannot fine tune the method so far to make it scalable. But thank you so much, Mustafa.
Thank
Thank
you
you so
for
much for
your
your question.
Thank you for your great answer, by the way, Krishna.
Thank you.
Okay. If you
Krishna, I have a question.
Sure,
It was
go
very
ahead.
good presentation. Thank you so much. And I worked in this topic on my last internship. That's why I listened with curiosity with you. And I have a question. You talk about carbon cutting, and what is your source? Maybe you talk about what.
Yes.
Is it sucrose or glucose? We used sucrose in laboratory.
Yes. So I directly add sucrose before ball milling to my precursor itself so that the carbon is induced within LMFP and forms a amorphous coating. But papers have claimed to use beta glycs. It's a complicated name, and it's just a more expensive form of carbon, and it just allows a much uniform and much even coating above LMFP particles. So that would be the very opt carbon source that most of the paper use, but we use sucrose because it's cheap and it does the job.
Yes, I guess it. Okay, thanks so much.
Yeah, thank you.
By the way, guys, Mustafa is interested in carbon synthesis. I hope he will have presentation for us about it. He and his team right now they are working on making some active carbon. So I don't have so much information about that, but I'm really excited to see his team and his works.
Okay. I hope we can do it. By the way, with the help of all of our presentation, we are completing the part of the cathode, also the anode, because generally the anode materials are carbon-based materials, and the cathode materials, which we are learning right now from Krishna, and we are completing the circuit.
The full cycle.
Yes, hopefully. So
Okay, Matt. If you do not have any question, we can finish at the time. And before we conclude the presentation, we would love to hear your thoughts on your video. And if you like to join our group, feel free to contact us through the comments section. Okay, thank you so much again.
Thanks so
see
much,
you
guys. Have a great day. Bye-bye.
Have a good
next week.
Thank you, guys.
Thank you, Krishna.